Let's see where we left off. So I think we left off with example 8. So example 9, the slope field for a differential equation is shown at the right. Which statement is true for all solutions of the differential equation? For x is less than 0, all the solutions are decreasing. So if you circle everything that has an x value that's less than 0, I'm going to actually get a different color to highlight where the actual x and y. This is the x-axis. This is the y-axis. Didn't do a great job highlighting, but got the idea. For all x's that are less than 0 over here, all solutions are decreasing. Are every one of these slopes negative? Well, no, obviously not, right? So that can't be true. Now look, when you're on a multiple choice, eliminate, eliminate, eliminate. So now we can eliminate this option, and we can eliminate that option. So now we're down to a 1 and 3 if we have to guess. All solutions level off near the x-axis. So no matter where I jump in, will I eventually level off at the x-axis? So if I jump in here, yeah, looks like it, huh? If I jump in back here, I still curl down. Everything, no matter where I start, those slopes always have me dropping into the x-axis. So yeah, I'm going to put a little check mark next to that. That guy is good to go. So we can eliminate 3 only. Can't just be 3 because we know 2 works. Now we're down to a 50-50 for all y's that are greater than 0. So that's all these. For all y's that are greater than 0, the solutions are all increasing. Yeah, that makes sense, right? Those are all positive. So we can put a little check there. So it's 2 and 3. So now we can box. Eliminate that other one and box in the correct answer. The slope field for the differential equation, I wouldn't want to try to plug into that. I'd use my calc for sure. Write a little program that would do it for us. But it doesn't ask us to sketch the slope field. It wants us to find the vertical segment. So what do you think these vertical segments are equivalent to? Hopefully you said vertical tangent lines. And when do we have a vertical tangent line? If what's true? If dy dx equals 0? No. That's where we would figure out if our function has a critical value. For you to have a vertical tangent line, the numerator needs to not be 0, and the denominator needs to be 0. This goes back to our rational function stuff that we did way back in the day. So I need my numerator to not be 0, my denominator to be 0. So I'm going to first figure out where my denominator is 0. Now we're not going to be able to get a nice little answer here like x equals or y equals because we've got x and y. So we're just going to try to solve for one of the variables. 2y equals negative 4x. Divide by 2, we get y equals negative 2x. That's one of our options, so we think that's got to be it because none of these is not an option. But let's say that if none of these was an option, you'd have to check, does that equal 0 when you plug in y equals negative 2x for those y's? In this case, it doesn't. It can't. If it does, they asked a poor question. What are we up to? Example, was that 9? Wait, was that 9? No, it's 10. Okay, I was going to say, what the? Example 11, ooh, another multiple choice. Look, Corpy has this on his iPad, so it's really easy for him to see. I would recommend trying to highlight the actual x-axis and y-axis for us. We have to use his printouts, so we can't quite see it as well. All right, now let's run through it. If y of 0 is greater than 0. All right, now I had to think through this a little bit, and I had to watch the video to understand what it's asking. It's saying, I'm going to circle this and draw a little arrow. Now we know what has to be true. This is a guarantee. So we're saying for all the x's where y is 0. Okay, so that's going to be all these, right? All these x's, my bad, I said that wrong. When all the x's are 0, that's all these y values. but we're only going to pick the y values that are greater than 0. X equals 0 and y is greater than 0. So if I was to look at that over here, I would circle where x is 0 and the y's are greater. Remember, this is the x-axis. So these are the positive y's and these are the negative y's. These are the y's that we're talking about here. Those are all the x equals 0 with y's that are greater than 0. It says the limit of the function. Now, this is the overall function. This is the actual curve. What would happen to the limit of the particular solution as x goes towards infinity? Well, let's drop in and draw one. So if I drop in right here, my graph looks like they're leveling off to some sort of a horizontal. Kind of looks like a horizontal here and goes up like that. And then if I drop in here, it's going to look something like this and something like this. As x goes towards infinity, are these graphs leveling off at 0? No, they are not. So we can eliminate that one. That one's out. Okay, the next one. You have to really think these through, and myself included. If x is, this is saying x is 0 and y is between negative 2 and 0. So that's all of these values. That's where x is 0 and the y values fall between negative 2 and 0. So this is negative 1, that's negative 2, negative 3, negative 4. Then the limit as x approaches infinity is negative 2. So let's drop in again. Now we're on the other side of this sort of curling. So I'm going to drop in here. It looks like it does. I'm going to drop in over here as I go towards infinity. I don't really care what's happening. I think something like this is happening on the other side, but I don't really care about that. So yes, I would say this one is true. Check or circle or whatever you want to do to indicate that that one's good to go. And then what could I use as a last color? I guess a yellow. No, I'll use my light purple. Okay, so now this is saying x is equal to 0 and y is less than negative 2. So that's all of these. The limit as x approaches 0. Let's see. So let's drop in here. Let's drop in here. Let's drop in here. No. Look at where do they level off? They level off again at they level off again there at negative 2. So it's kind of confusing. The way they drew it, you might be, susceptible to just looking at the graph and saying, "Oh, yep, there's my y-axis." No, or x-axis. No, that's not true in this case. You got to be a little careful. So which one? We only knew that 2 was the only one that was good to go. So 2 is our answer. Okay, these next, so the rest of the notes here, 12, 13, 14, 15, all the rest of these, they're all just free response questions. So I'm not sure which ones I'm going to do in class yet, but I'm going to go through and do all of these. So if I didn't do this one in class, maybe you want to skip it or you want to try it on your own and then compare back to me. The big difference is I'm going to give you the slope fields just because I know you can do it and it just takes forever to draw the slope fields. So let's go through this first one and sketch all the slope fields first. So these on the x-axis and on the y-axis, all those values have a slope of 0. I'm actually going to write them there for myself more when I go forward next year. I can look back and don't have to recalculate all those on my calc. And then the ones, so this one is a slope of 1. This is a slope of negative 1. This is a slope of 1. This is a slope of negative 1. Down here, these are slopes of 1. These are slopes of negative 1. This is a slope of a half. Like I said, you don't have to be perfect. It's just got to be decent. This is a slope of 2. This is a slope of negative half. This is a slope of negative 2. This is a slope of negative half. This is a slope of -2. Positive half, +2. So like I said, I know you could do that if you had the time, but look at that. What's that? Freaking 20 points, 25 points that, yeah, which we could do. Let's just say, right, let's cut out that part. Let f be the function that satisfies the given differential equation. That always is talking about this. Write an equation for the tangent line to the curve f of x, y equals f of x through the point 1, 1. That's easy. That's really easy. This is our dream scenario on the AP test that they ask us to find the tangent line equation. So the tangent line, I'm going to write it in Taylor form this time, y equals 1. Now, I need slope, right? I need slope and a point. Well, I got the point. Well, I need the slope. What's the slope at 1, 1? Folks, that's what this is. This is what we just did. The slope at 1, 1 was 1/2. So plus 1/2 times x minus 1. There's the answer to part A. Then they want us to use the tangent line to make an approximation. So we're going to do one of those tangent line approximations that we did a couple units ago. So remember, anytime you see estimate or approximation, you are on squiggle alert. Squiggle alert. So I'm going to have some squiggles here. F of 1.2 is approximately, and then I'm going to use the tangent line as an estimator. 1/2, 1.2 minus 1, which equals 1 plus 1/2. 1.2 minus 1 is 0.2. Half of 0.2 is 0.1. 1 plus 1.1. Good. Find the particular solution. That means that this, if we're trying to find the particular solution with an initial condition exactly, they didn't say make a sketch of the particular solution. We're actually trying to find it. That means that this must be a separable function. So you'd have to be able to get this where y's and x's are on different sides. So let's do that part first. Actually, I would encourage you to pause here. Try to do it on your own. Let's see how you did. So I'm going to separate, first of all, that's 1 point right in of itself. So I'm going to bump the y to the bottom. I'm going to bump the dx to the top. So I would have 1 over y dy equals x over 2 dx. Now I would integrate both sides. I wish I would have done green there. Oh well. Then we get natural log of absolute y equals add 1. That's x squared, divide by. There's already a 2 down there, so that becomes 4. Okay, I've got to get natural y by itself. So I'm going to get rid of the natural log with an e to the. I'm not going to show my work. E to the would leave me with absolute y equals e to the x squared over 4 plus c. Now, this is that spot that you could go two ways from here. If you want to, you can get rid of the absolute value by making this a plus or minus, and then you've got to come back at the end and double check to see if it's a plus or minus. Or you can use that trick that we talked about last lesson. So I'm going to do the trick. That's where I break up e to the something plus something else. So in other words, I'll write it over here. E to the x plus y is equal to e to the x times e to the y. So we can break this up into e to the x squared over 4 times e to the c. Well, c is some constant. E to the c is some other constant. So now we don't need to worry about that. So absolute y is equal to, I'm just going to write it as c times e to the x squared over 4. And now when I do the plus or minus, the plus or minus gets absorbed into the constant, which we don't know what it is anyway. So c e to the x squared over 4. This is what we call the general solution. Now, I clearly don't have enough room here. I'm running out of room. So now we want to, actually, I'm going to squeeze it down here. I've got some room down there. But we still need to use this to find the particular solution. So now I'm going to take this. I'm going to do a little work down here. So we have to figure out what C is when X is 1 and Y is 1. So 1 equals C times e to the, let's put 1 right in there, e to the 1/4. So I would divide both sides by e to the 1/4, and I would get 1 over e to the 1/4 equals C, which could also be equal to e to the negative 1/4. So then my actual answer, my particular solution, would be y equals e to the negative 1/4 times e to the x squared over 4. That would be my particular solution. Use your solution to find f of 1.2. Good night. Okay, so I'll do that over here. F of 1.2. This isn't an approximation. This is an equals. So that'd be e to the negative 1/4 times e to the 1.2 squared over 4. Good night. We did not expect you to do that by hand. This turns out to be 1.116. Okay, so what was our estimate? So they want us to compare your, so this is the actual answer for f of 1.2. That should really be up above, but so be it. The actual answer here is to compare our estimate, which we found of 1.1, to our actual of 1.116. Pretty good. So our estimate was an underestimate or an overestimate. It was an under. So that makes sense because if you go back to our function, let's see if we could do a sketch here. What was our initial condition? 1, 1. So at 1, 1, let's see how crappy I can draw this thing. So this thing needs to be going out like this and then levels off. So this, maybe something like this. Gosh, I don't know. Maybe something like that. I'm going to graph it on here to see what it actually looks like. So e to the negative 1/4 times e to the x squared over 4. How do we do? Hey, joy. So why does it seem reasonable that I don't know if that was on there or not, but yeah, this should be an underestimate because what do we know about our function? In that area, our function is concave up. So our little argument is we're going to use the slope field to explain why. Ooh, I don't know if I can use the slope field. I might just say the estimate from part B was an underestimate because F is concave up. How about on the interval 0 until 2? That gets me something decent, I guess. I didn't mention the slope field, so that I'd lose a point there. How would I talk about that? I'd have to talk about I have to look at the second derivative. I might have to look at the second derivative. I'm not sure. So, sorry. Okay, like I said, we're going to keep going. I'm going to keep doing these for my video, and then people can watch them if they want. So, on the axis provided, do the slope field first. I'm going to help you out with our slope field if you want to do it on your own. Actually, no, this would be a good one to try on your own. This is one I think I'm going to be doing in class. So, yeah, if this is something I didn't really talk about up to this point, if you're having a hard time finding the slope field, take the actual x and y value, like let's say 0, 0, and then draw a little arrow of what you get when you plug them in. So that's 0, 0, that's -1. So here I need to have a slope of -1. Then pick another y value, let's say 0, 1. 0, 1, that would be 0, that would be 1, 1 minus 1 is 0. So I'm going to have a slope field of 0 here. 0, 2. If you can't do it in your head, there's no shame in that. 2 minus 1 is 1. Just take your time and make sure you get the right answer. That's what's more important. 1 and 0, that would be 1/2. Take away 1, which would be -1/2. So that would be -1/2, something a little bit more flat. 1, 1. That'd be 1/2. That'd be 1. That'd be 1/2. So a little bit less flat. 1, 2. 1, 2 would be 2 minus 1. That would be 1 and 1/2, so 1.5. So that's something bigger than 1. And then we go the other direction, -1, 0, -1, 1, -1, 2. -1, 0 would be -1/2, minus 1 would be -1.5. So I want to try to make that a little steeper. -1, that would be -1/2. That'd be 1, take away, that's -1/2. Or should that be, yeah, -1/2. That's all right. Then -1, that'd be 2, that'd be 1, that'd be 1/2. It looks right. The only one, yeah, those were, yeah, it always has some symmetry going on. So it's good if you have some things symmetrical looking on there. All right, so find the second derivative in terms of x and y. So that's nice. That means that we can just take the first derivative and derive it again. We don't have to try to get y or x by itself. So we're going to do some of that. What kind of differentiation is it when you have x and y together? Hopefully you remember that was called implicit differentiation. So I'm going to derive this again. So that would be d2y dx squared equals the derivative of 1/2 x according to x is 1/2 plus the derivative of y according to x is 1 y prime, because we still have to do that. So I'm going to write it this time as dy dx. Then minus 1, derivative of -1 is 0. So what are we supposed to do with this? Well, if you stop here, you're in real trouble because you have dy dx and d squared y dx, the second derivative. But look, dy dx is equal to this thing. So we can now sub that in, and we would get 1/2 plus 1/2 x plus y minus 1. Now I would clean this up because I like things to be nice and neat. So I would then say my second derivative is equal to 1/2 x plus y. Then 1/2 minus 1 is -1/2. So there's our derivative. Now we need to describe the region in the xy plane in which all solutions to the differential equation are concave up. So tell me what you know about a curve. What has to be true for f to be concave up? What do you have to know about f for f to be concave up? Let's pause it if you need to think more. But f is concave up f is concave up if f double prime is greater than 0. So we need to now figure out where f double prime is greater than 0. Well, look what we just figured out. We just figured out what f double prime was. So let's take f double prime and figure out when it's greater than 0. So 1/2 x plus y minus 1/2 is greater than 0. Generally, how do we want to define things? Usually we like to have y by itself, so simply move stuff around. Negative 1/2 x minus, no, plus 1/2. Okay, so everywhere, every y value that is greater than, plugging in x into this and getting whatever, greater than this, what is this thing if I asked you to graph it? That would be a line. So any y values that are greater than this line is going to be the region where our function is concave up. Now look, you can't just say this. You have to actually write out a little bit of an argument that says what you're thinking. So how did they say it? They said describe the region in which all the solution curves to the differential equation are concave up. All solution curves to the differential equation. Huh? You see what I did there? See what I did there? Huh? Just took their thing and wrote it right back to them. Are concave up. Are concave up. I don't know if on the actual test you should write it out. I don't know how picky they'll be about that. I would say you should. All solution curves to the differential equation are concave up if how do I want to finish this? All solution curves to the differential are concave up. How about if I just say above the line y equals negative 1/2 x plus 1/2. There we go. Alrighty, let y equal f of x be a particular solution. So that's usually a sign that we can figure out the actual. Oh, no. We can't, we won't be able to figure that out, will we? Because we can't separate, like I would try to separate variables. But look again, when I try to separate variables, so I would move I'd have to multiply by dx first, let's say. I wouldn't have to do that, but I'm choosing to. And you'll see where the problem is. Then I'd have to distribute this to get it into the y, and then I'd have to move it over, so I'd have a dx and a dy on the same side. So this is no good. We can't separate variables. So we have to come up with something else. So we want to figure out the particular solution. So this function that we're talking about is one of the solutions in this slope field. Initial condition is f of 0 equals 1. Does f of x have a relative min, a relative max, or neither at 0? So what do we know about where relative mins or maxes occur? So go back in the old time machine. F has a relative min, a relative max when f prime does what? Switches from positive to negative. I'm going to cross out the min here. We'll just look at one case and just remember, for max, and then min would be negative to. Okay, can we tell that from our slope field? Can you guarantee, so remember, what are we hitting at? F of 0 equals 1. This is our point. F of 0 equals 1. That's where we're looking. Can you guarantee? Now, life is good in a little bit. Like, there's one thing that I can guarantee. What can you guarantee that is occurring at 0, 1 for the function? F of 0 equals 1 is a what value? This is definitely a crit value. This is a crit value because f prime of 0 is equal to 0, right? At this y value, what's your derivative there? Is 0. So that's good. We at least know it's a crit value. Can we tell if we switch from positive to negative? Can you guarantee right to the left and right to the right are going to be switching signs? We can't guarantee that. So is there any other way that we can decide whether or not, so here's another sad face, because we can't tell for sure if f prime switches from positive to negative. We think it does. These are all negative. This has a negative slope. Well, wait, but that has a positive slope. And then this has a positive slope, but that has a negative slope. So actually, we don't know. This is a lot harder than we thought. So is there another way that we can determine whether or not a function has a min or a max? Well, yes, Mr. Stuckey, there absolutely is. F has a relative max, and I'm just doing max again. Min would be just follow logically from there. F has a relative max at x equals c if what two things have to be true? First of all, it has to be a crit value, so f prime of c has to be 0. And, I should say not or, and what else has to be true? Well, this was that second derivative test that we didn't really use all that much. And f double prime at that place has to be, so if it's a max, it has to be less than 0. So can we prove that f prime, we need to justify. So can we prove that f prime of c equals 0? Yeah, let's just prove it. And the way we evaluate that is you write it like this. You write dy dx evaluated at 0, 1 equals. So in other words, go up here to your function. Do we have it anywhere else? Yeah, we could put it in right here. There's dy dx. Put 0, 1 in there. 0 gone, 1 minus 1, that's 0. Comma, what's the second derivative evaluated at 0, 1? But we just figured that out here. There's our second derivative. Let's put 0, 1 in there. That's gone. 1 minus 1/2 is 1/2, which is greater than 0. So let's do a little argument like we always did before. So f has a relative. Ooh, wait. So is it going to be a min or a max? So since this was negative, this thing's going to end up being a min. F has a relative min at x equals 0 because f prime of 0 equals 0 and f double prime of 0 is greater than 0 or positive. It's pretty slick. Find the values of the constants. This one is actually a ton easier than it looks. Is there any place where we figured out a solution that was a linear? Remember what we did right over here? Right? Don't overthink this one. So I would say something like this from, what was that, part B? The linear solution was y equals negative 1/2 x plus 1/2. So m, remember they're asking for m and b. So m would be 1/2 and b would be, m would be negative 1/2 and b would be 1/2. So we already actually did that. That's the one. Corpy describes these as like the questions or the ones where you got to think a little bit more, but it's usually something that relates back to some work that you've already done. Boy, I'm going to stop the video here and then I'll continue it just to save us some watching time.